Okay, let's just get going. So, we are talking about Cauchy integral formula, right? Yeah. And what is the statement of Cauchy integral formula? Cauchy integral formula. Says the following, that if we have f, this, complex numbers, holomorphic, and we have that the ball of radius r of z0 is contained within omega. Actually, its closure is contained within omega. Then we have that f of z equals 1 over 2 pi I, the integral around the boundary of the ball of f of zeta minus z d zeta for any z inside the ball. Okay, give me a sec. For any z inside the ball of radius r around z. Okay, so this is the statement that we have, right? Yeah? And we learned what this meant in the context or in the situation of putting the z exactly on the z0. So here's the picture. We have some ball like this, some radius like this, right? And we took some z inside this, yeah? And we can find out what this value is just by integrating around the boundary of the ball this weird-looking expression, yeah? And in a particular situation, when you took z equals z0, then this thing just reduced down to taking the average around the boundary of the ball of the real value part plus I times the average around the boundary of the ball of the imaginary part, yeah? That's what we found out, yeah? So the meaning of this is very natural or very understandable in the case when we stick in z equals z0 into this formula. Yeah? And later I will show you actually that this formula can be deduced from the mean value theorem. So it looks a little bit kind of just complicated and unnatural when you first see it. But it is just, at its heart, the mean value property for the real and imaginary parts. And that follows because they are harmonic functions, and we'll talk about that later going forward. So this is one of the key formulas we're going to have in this course. It's one of the key identities. It's going to give us an incredible amount of stuff. And the first thing we're going to do, of course, is just to prove it. So how are we going to prove this? Well, we're going to use the stuff that we've learned already. So we have some point like this, z, yeah? And we are going to create a keyhole contour. Actually, maybe I need to create a bigger picture. Let me do a bigger picture like this. Okay. This is z0. We have some z like this. And we're going to create a keyhole contour like this. We're going to put a little circle around here of some small radius, and then we're going to go up like this and up like this. Okay, and we're going to let this thing be delta. Okay, and then we're going to go around like this, like this, like this, like this, like this, like this. So this is our keyhole contour. Let's write this way around. All right, so notice that we're going anti-clockwise around the bigger circle, and then we end up going clockwise around the smaller one. Yeah? Cool. All right, so first claim is that this keyhole contour be denoted by gamma of delta alpha, where alpha is the width of the small little circle here. Okay, this is our keyhole contour. And our first claim is that when we take this function like this and we integrate over the keyhole contour delta alpha, f of zeta over zeta minus z dz, yeah, we claim that this is equal to 0. Tell me why this is true. Why is this true? So we're thinking of this as a function of zeta. Z is just fixed, right? It's this ball here. So is our theorem inapplicable because we consider this function, f of zeta over zeta minus z? Does that mess things up for us? How would it fail? How would it mess it up for us? It would mess it up for us if this function here failed to be holomorphic, yeah, on the closure of the interior of this keyhole. Yeah? Is that the case? Does this thing fail to be holomorphic on the closure of the interior of this keyhole? No, because the only problem we have, the only issue was when zeta is equal to z, right? Then we have a singularity. But this keyhole avoids that, right? So on the interior of this keyhole and on the boundary of this keyhole, it's analytic, right? Yeah. In fact, we can just apply this theorem. So this closure of the interior of this keyhole is inside a domain on which this function is analytic. Yeah? On which this function is analytic. Yeah? Cool. So by the previous theorem, this is true. Is analytic on interior of the keyhole closure. Cool. So that is kind of a nice thing, because what does that mean? Well, if we look at this somewhat carefully, what we see is that it doesn't matter how small delta is, right? This remains true no matter how small delta is. Yeah? So it's also true. So we take the limit as delta tends to 0 of this expression this thing is equal to 0, because it's equal to 0 for every single delta. Yeah? Cool. All right, now look at this expression here, the limit of this integral. What will the limit of this integral be? What happens as we let delta tend down to 0? What do we get out from that expression? Indeed, why? Why so? Yeah, because alpha's fixed and we're letting delta get smaller and smaller and smaller, right? So what we're doing is we have this function, which away from z is a perfectly nice differentiable holomorphic function, right? And we're integrating from here to here, and then later we're integrating from here to here. Yeah? And if these things were exactly on top of each other, we would know that they would cancel out. Yeah? But they're not quite. They're not quite on top of each other. There's this tiny delta. But being a differentiable function, it's also continuous, right? It's also continuous. So the difference between the integral from here to here, as opposed to the integral from here to here, yeah, if we, i.e. in the same direction, so the integral from starting here to here compared to the integral starting here to here, yeah, the difference between those integrals is incredibly small, right? It gets smaller as delta goes down to 0 because, again, f is, or this expression here is continuous. Do you see what I mean? Yeah? So in the limit, this entire thing will just reduce down to the integral of these two circles. Now, I can add more details if this isn't clear to you. Do this if you want more details. Okay, let's do some more details. So without loss of generality, we can assume that this line segment is on just the real line, and the one next to it, which is parallel, is just up a little bit. Yeah. So consider this. Consider a holomorphic function h, where we take the integral from, say, 0 to some a of h of z dz minus the integral from I times delta, and then a plus I times delta, and we're going from this to this, this to this, in this direction of h of z dz. Consider that. Yeah? We can just give ourselves a parameterization. So the parameterization we'll just do here will be just z of t is just equal to t, because we're going along the real line. That's the easiest choice. Yeah? And the parameterization here we'll do is z of, or let's call this one z1, let's call this one z2. So z2 of t will just be I times delta plus t. Yeah? Because we have this line, and then we have the line which is just a little bit above it. Yeah? So then these guys turn out to be the integral from 0 to a, yeah, just h of t dt, yeah. Let's go to our first parameterization. Let me put it up here. So we're taking the parameterization z1 of t is t. That does the first job. z2 of t is equal to I times delta plus t, yeah. And the derivative of both. So we're using these two parameterizations right here, and the derivative of both of them is just equal to 1. Yeah? Yeah? So then this thing here turns into this thing, and this thing here turns into the integral from 0 to a of just h of t plus I times delta dt. Yeah? Cool. So then what is this? If we take the absolute value of this, it's less than equal to just the length that we're integrating over, and then the supremum over the difference between h of t minus h of t plus I times delta. And I know that's hard to read off the edge there, where t belongs to 0 to a. Yeah? And everything is continuous, right, inside an open set that contains both of these intervals. Yeah? So we can just let t go down to 0. Yeah? So again, we just let delta go down to 0, and then this quantity has to go down to 0. Yeah, because if it wasn't true, then we'd just pick a subsequence for which was false, extract a subsequence which converges and would contradict continuity. Are you everyone with me now? Okay. So we do indeed have that as we let this delta go down to 0, these lines will ultimately just cancel each other out. Yeah? So all we'll end up with is this integral like this, going clockwise around the little circle, and the integral around the big circle. That's all we end up with. Yeah? And going clockwise around the little circle is the opposite orientation, so it's a minus. It's minus the normal integral going anti-clockwise. Yeah? So this thing is equal to 0, but it's also equal to the integral integral of the boundary of the bigger circle, which is radius r, around z0, right? This expression, f of z, or f of zeta, minus zeta minus z, d zeta, yeah? And then minus the integral of the little circle. And the little circle is radius alpha, but now it's around z, not z0. Yeah? So in other words, what we have is that the integral of this thing is equal to the integral of this thing. I should say that better. This integral is equal to this integral as a consequence, yeah? So we start off with an integral around the bigger circle, and we end up with an integral around the tiny, tiny circle around our point z, yeah? Cool. So I'm going to raise the board, and we're going to see how that helps us. So try to remember that we've reduced this integral here, to the integral around a little circle around z itself. Z we've chosen as just some point inside the ball B. We were to the point of understanding that the integral 1 over 2 pi I, the integral around the bigger ball BR of z0 of f of zeta minus z dz is the same as 1 over 2 pi I, the integral around this little ball, be alpha, now around z, not z0, of this thing, f of zeta minus z dz. Okay? Now, let's make a trivial adaptation to this. Let's write this as f of zeta minus f of z plus f of z, which for sure we can do. We can add and subtract something without changing anything, yeah? The zeta, yeah? That's clearly true, yeah? And then let's break up that thing. So that thing is 1 over 2 pi I, integral around the bound with the ball of radius alpha of z, and then this thing, f of z minus f of zeta minus f of z, zeta minus z, d zeta, and then plus this thing, right? The 1 over 2 pi I integral around the boundary of the ball of radius alpha around z, now f of z over zeta minus z d zeta, yeah? Okay, cool. Now notice, f of z is the number we chose at the beginning, right? Inside the ball. We're doing all the action, all the integrations in terms of zeta, yeah? So this thing we can just pull outside the integral. We could just pull it directly outside, yeah? Let's do that. So it is not part of the action of the integration. It's just a constant for our purposes. Let's just pull it directly out. So this is 1, and then this thing here is just f of z. Yeah? Cool. Now, let's try and understand this expression here in the blue box. So in the blue box, what do we have? We have f of z over 2 pi I, and then just the integral of this function over the ball. But this is a function that we can easily just actually calculate, putting in a parameterization. So the obvious parameterization around the ball is the one which you would, you've told me before. Let's just take z of t to be equal to z plus alpha e to the it. That's a nice parameterization of the ball of radius alpha around z, yeah? And what is z prime? That is equal to I times alpha e to the it. Yeah? Cool. So let's directly calculate what this thing in the blue box is. So integrating from 0 to pi. Like this, and then we put in the stuff. So we're going to have 1 over, now zeta, we're going to write it's going to replace by z of t, and it's equal to this thing, so the z's cancel. So over here, we're going to have alpha e to the it. Yeah? And then we're going to have z prime, which is equal to I alpha e to the it, like this. And we're integrating with respect to t. Yeah? So this thing turns into this thing when we use this parameterization z of t. With me? Yeah? Cool. And then we notice that this alpha e to the it and this alpha e to the it just cancel. Yeah? Yeah, they just cancel. So this is just equal to the integral of 1 from 0 to 2 pi, not pi, to 2 pi, going all the way around the circle. Yeah? So this is just the integral of 1 from 0 to 2 pi, just equal to 2 pi. Yeah? So this thing here just ends up being 2 pi. Yeah? And that's going to cancel with this 2 pi over here. Oh, not quite 2 pi, it's 2 pi I, because this I remains. Yeah? So this 2 pi I is going to cancel with this 2 pi I underneath here, and then this thing just does indeed just give us f of z. Yeah? So the stuff in the blue box is actually the stuff that we want, right? Stuff that we want. Yeah? But we have this other term. We have this other term over here. So let's look at this. Look at this guy here. Yeah, what are we doing? We are integrating this function, yeah, around this small ball. Around this small ball. Yeah? Cool. All right, so what would happen if we parameterize this? So let's put a line here, and let's do the red box over here. What would happen when we parameterize it is we get 1 over 2 pi I, and then the integral around 0 to 2 pi. And then we're just going to have this expression here. So we're going to have f of z plus alpha e to the it minus f of z. And then on the bottom, we are just going to have just alpha e to the it. And then this is multiplied by, let's put it over here, z prime of t, and z prime of t is this thing here. So it's just I alpha e to the it dt. Yeah? Cool. All right, so tell me about this. Let's change color. Where's my blue? Tell me about this thing here. As alpha gets very, very small, what is this thing here tending towards? Just the derivative, right? Because it's a differentiable function. Yeah? So if we insist that alpha is small enough, then this thing minus f prime of z is less than any epsilon that we want. Yeah? Yeah? And in particular, this thing will be a bounded expression. It'll be a bounded function over the circle of radius alpha around z for some small enough alpha. Yeah? Because it's within epsilon of this particular fixed complex number, f prime of z. Yeah? Yeah? So we can, for example, find alpha small enough so that the absolute value of this thing is less than twice f prime of z absolute value. Yeah? Because it's less than, it's because it's as close as you like to f prime of z plus some error of order epsilon, right? Yeah? So we can guarantee it's less, the absolute value of this thing is less than twice the absolute value of f prime of z. Are you with me, everybody? Give me a thumbs up if you're with me. All right, cool. So this thing for small enough alpha is just a bounded thing. It's bounded explicitly by something we know, twice the absolute value of f prime of z. Yeah? What about this thing? Well, this thing is just a complex number whose absolute value is equal to alpha, right? Yeah. So we're integrating something from 0 to 2 pi multiplied by a bounded thing times something which is absolute value bounded by alpha. So if we take absolute values through inside this thing, so if we take this thing is less than the absolute value of everything inside here, yeah, then that is going to be less than just 2 f prime of z. I should write 2. Well, we're going to have the 2 pi will cancel with the 2 pi. So this is going to be less than equal to this thing times just alpha, like this. Yeah? So as alpha tends to 0, this entire expression tends to 0. Yeah? Which tends to 0 as alpha tends to 0. So the red box, this thing, will just tend down to 0 as alpha goes down to 0. Yeah? And since we have that this formula is true for any choice of small alpha, this means that this thing, yeah, is actually just equal to this thing, yeah, which we showed was just equal to f itself. Yeah? Cool. Yeah? Because alpha can be made as small as we like. So this thing is not going to play a role. Yeah? Formally speaking, for any epsilon bigger than 0, we can show the difference between this and this is less than epsilon. And it's true for every epsilon less than 0. So these things are actually equal. Everybody with me? Give me a thumbs up. Okay, cool. And that's it. That's the proof of the mean value theorem, right? We've shown that this is equal to this. Yeah, and that's true for any z inside the ball. All right, so the best way to convince you that this is really a big deal is to straight away go on to one of its most important consequences, which is the following theorem. Suppose f is holomorphic on omega, then f has any order of derivative. It's infinitely differentiable. Yeah? And we actually have a formula for the derivative. We have that the kth order derivative at z is equal to k factorial over 2 pi I, the integral of the boundary of the ball z0 of f of zeta over z minus zeta minus z to the k plus 1 d zeta, like this. So when k equals 0, then this is exactly Cauchy's integral formula. Yeah? But now this gives us a formula for the kth order derivative in terms of an integral of the function itself. Okay? Yeah? Which is, again, a very powerful thing. So derivatives get worse. The more you differentiate something, the worse it gets. You take you'll take your innocuous-looking function, say the square root of x, you differentiate it, you instantly have something with a singularity at 0, right? Differentiation makes things worse, right? And what this thing says is that actually by doing this thing, which is a smoothing thing, which is to average over something, to integrate over something, we do this smoothing thing of f, and we actually get the derivative. So in one of some of the things I do involve regularity of partial differential equations, and something we battle with all the time is try and control higher derivatives with lower derivatives. And when we get some pathetic little bit of control of a higher order derivative, even a fraction of a higher order derivative with a lower order derivative, we're very excited because that's some progress. So this is really, really strong to be able to explicitly give a formula for the higher derivatives in terms of the function itself. This is a very strong thing, as we'll see later. And the first part of the statement is also extremely striking. So what does it say? It says that if we have a function that is holomorphic, which means it just is one-time differentiable, then every order of derivative exists. It's 2 times, 3 times, 4 times, whatever number of times differentiable, it is that number of times differentiable. And we have an explicit formula for what the derivative is. So I told you that calculus for functions from the complex plane to the complex plane bifurcates dramatically from calculus from the real line to real line. And this is the initial point of bifurcation. So it's absolutely false that we have something like this is absolutely false on the real line, right? If you have a function that's one-time differentiable on the real line, that doesn't imply anything else, right? It doesn't mean it has to be 2 times differentiable or anything else, yeah? In fact, we have entire classes of functions. We have the CK functions that are k times differentiable with continuous kth derivative, right? As you might be learning in real analysis. This says that there's no such thing as a CK function in complex analysis. It's a pointless thing to define because CK is the same as C infinity. Right? If you can differentiate it even one time, you can differentiate it as many times as you like. Yeah? So as soon as you have differentiability, you're smack in this world of incredibly regular functions. Yeah? And what we're going to be doing in complex analysis is talking about differentiable functions. So instantly from this theorem, we have just all the regularity we could possibly want just given to us in one go. And that's one of the reasons this subject is has so many powerful theorems that are so easy to prove, is that all regularity issues just vanish as a consequence of this statement. Okay? So this is a very significant theorem. This is a very important theorem. And it's going to follow reasonably easily from Cauchy integral formula, because Cauchy integral formula is writing a function in terms of integrating the function around something. So we're going to do the natural thing. We're going to just differentiate through, right? And it's going to turn out that we can figure out what that means, and we're going to get all the higher order derivatives, and you'll see that in a second. So with a bit more experience in analysis, you can sort of anticipate that a formula like this gives very good stuff, because integrating something is regularizing in itself. All right, so we're about to prove this. Question for you people. Do we know that F has a Taylor series now? The answer is no. The answer is no. Yeah. Because we have this function that was non-trivial that I presented to you, right? Or I asked you in homework, and I asked you to show that the derivatives of all orders was equal to 0. Yeah, which wasn't an easy thing. You all work quite hard to try and do that. Most of you had pretty good arguments. So that means that function obviously cannot have a Taylor series. If we had a Taylor series, we'd be able to expand it around 0 in terms of the coefficients, which are the higher order derivatives divided by whatever factorial. Yeah. But all the higher order derivatives was 0. So that function can't possibly have a Taylor series. Yeah? So having something which is infinitely differentiable does not in itself mean that it is analytic, that it has a Taylor series. Does that make sense? Cool. All right. But it turns out that these functions actually do have a Taylor series, and that's another thing that we will prove from Cauchy integral formula, but it doesn't follow yet from this. So there is in analysis for, or calculus or analysis for functions from R to R, the class of functions that are C infinity, infinitely differentiable, is a much wider class than the class of functions that actually have a Taylor series. Yeah? But these guys, these functions that are holomorphic, we'll find out they're even better than infinitely differentiable. They actually have a Taylor series, and we'll see that shortly. Okay, first, let's try and prove this. Well, let's actually succeed to prove it. Proof. So we know it's true for k equals 0, right? Right? So we're going to do an induction. We're going to assume it's true for k, and we're going to prove it's true for k plus 1. So assume for k, and we will prove it's true for k plus 1. So what are we going to do? All right, what we're doing, we will prove it's true for k plus 1. All right, so there's nothing to do but to look at this quotient, right? So we're going to take f of k of z plus h minus f of k of z over h like this. Yeah? We're going to take the difference quotient. And if we use the fact that we know that this is true for k, then we just put in this formula into this thing right here. Yeah? So this thing right here, so that means that we're going to have k factorial over 2 pi I, right? And we're going to have the integral around the boundary of the ball of radius z0. And then let's pull out this zeta like this. And then we're going to have 1 over z minus, or zeta minus z plus h. Zeta minus z plus h to the power k plus 1 minus 1 over zeta minus z to the k plus 1 like this, d zeta. Yeah, and I need the 1 over h somewhere. Let's put it here like this. Yeah? Cool. So we would like to try and understand what happens here. I'm going to raise the board. We had f of the kth derivative z plus h minus f of the kth derivative z over h, and it was equal to this expression, 1 over 2 pi I k factorial like this, and then the integral around the boundary of the ball radius r around z0, and we had f of zeta over h itself, and then 1 over z minus zeta plus h for k plus 1. Oops, no, the other around. This is zeta minus z plus h. To the k plus 1 like this, minus 1 over zeta minus z to the k plus 1 like this. That was our expression. Yeah? Cool. So what we'd like to do is obviously to take h going down to 0, yeah? And ignoring for the second the issue of passing the limit through the integral. That would mean taking the limit as h goes to 0 of this expression right here. Yeah? Yeah? And if we just think about this, that should be something that isn't too hard to understand, right? Because what is this? If we had this function, let's put it over here, if we had this function h of z was equal to 1 over zeta minus z like this, right? Then this thing, as we pass the limit as h goes to 0, inside this expression here, all we would get would be the derivative of h. Yeah, we just get the derivative of h. Oh, I forgot to write the k plus 1. Yeah, so the blue box, as h goes to 0, should just be the derivative of h. Can you see that? Yeah, with me. And then what is the derivative of h? The derivative of h, this, it's going to be minus k plus 1 over zeta minus z to the k plus 2, but then we also differentiate the inner function, which is minus z, and the minus cancels, so it gets to be this. Yeah? And that being true, that would give us exactly what we want, right? That would give us exactly what we want. Because in this k plus 1 would go over here, would have k plus 1 factorial. Yeah? And then we would have, instead of integrating this thing, f of zeta over zeta minus z to the k plus 1, it's now over k plus 2. So it would be exactly the inductive step that we want. So we can kind of anticipate that this thing is going to work out for us, that we are going to get what we require, if we can pass the limit through the integral, right? If we can pass the limit through the integral. So we have specific theorems to do this, and we'll be learning this in real analysis, something called the dominated convergence theorem. But I don't know, we don't need something as strong as that. What we need, or what we will have, is the fact that for small h, this thing will uniformly converge to its derivative. So in Stein, they do a more complicated argument where they write this thing like this. They say, okay, we let a be 1 over zeta minus z plus h, and let b be 1 over zeta minus z like this, and then the stuff excluding the h, so just take away the stuff here, the stuff in the new blue box like this is just a to the k plus 1 minus b to the k plus 1. And then they expand this out and they do this argument, which is the same way you prove the power law when you're trying to differentiate x to the n. And I thought, okay, they have this extra complexity because they're being very careful about passing the derivative through the limit. And now it occurs to me that it's just not necessary. So I was going to follow that proof, but now I'm wondering if it's just not better to be simpler about it. Okay, so let's look at this function. So z is like this. If we are away from zeta, then this is a perfectly nice differentiable function, right? So zeta lives around the boundary of the curve like this. Okay, zeta is going around like this. Z is somewhere inside like this. This is z0, yeah? So no matter what zeta is, there's always some definite distance between z and zeta, yeah? So as a function of z, this is a perfectly nice differentiable function, yeah? Because it's just a power, it's just a negative power, yeah? So we can differentiate it as many times as we like, yeah? We don't need to use the statement of the theorem. It's just clear to us it's infinitely differentiable. Yeah? So it is the case that the difference quotient will uniformly tend towards the actual derivative. That is indeed the case. And that will be true for every single zeta that we have around the outside. Okay? And the constants might be a bit different, but it'll still remain true as we move zeta around the outside. And I guess now I see why they did this, why they bothered to do this expansion, because you'd have to somewhat carefully think about the fact that this thing divided by h minus its derivative is as close as you like. It's within epsilon for any zeta around the outside. And I claim it's true because there's always some non-trivial distance. So you could actually argue this way. But they didn't. They chose to do it this way. Okay, so I'm going to do it Stein's way. I'm going to do it Stein's way, even though we can do it this way. What would be a really good homework exercise for you would be to actually prove this theorem in the way I've just talked about. Okay, so not using this expansion, just using the fact that the difference quotient, this thing minus this thing over h, is tending towards this thing. Yeah? And implicit in this is the fact that we have that our function h is defined in terms of zeta. It depends on zeta, right? Yeah. So if we had that, we could make the derivative of this minus the difference quotient is less than epsilon for every zeta around the circle. Yeah. Then we could pass to the limit, because when we have something which is uniformly converging around the thing we're integrating, then for sure we can pass through the integral. Is that making some sense to you? Okay, good. So I'm going to set that as a homework exercise, and you people give it a go. But avoiding that, let's do it the Stein way. So Stein says, let's look at this thing, and this thing, therefore it's the same as a to the k minus b to the k. Yeah? Cool. And this thing on the bottom here, we'll think about in a second, but first let's try and understand this. Well, we have the following nice formula, which is as follows. If we call this thing star, if we do this, if we take a times a to the k plus a to the k minus 1 times b plus blah, 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 a to the 1, b to the k minus 1, and then finally plus b, and then we subtract b times all of this thing. Well, the same thing, a to the k plus a to the k minus 1 is b dot is b. Then we get a whole bunch of cancellations, because when we multiply through, this guy will be the same as this guy, right? So we'll get a whole kind of massive slaughter happening. We'll have this is killed by this next term is killed by this. And the only survivors of this will be just this thing that we're interested in, will just be star, right? So what's that told us? That's told us that we have that a to the k plus 1 minus b to the k plus 1 over a minus b is this expression, a to the k plus a to the k minus 1, b plus blah, 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 a1, b to the k minus 1, plus b. Is that making sense? Yeah? So if you've taught calculus and you've taught how to prove the power law before you have log differentiation, this is the trick. Yeah? And it's just noticing that as you multiply this thing through and you multiply this thing through, we get a huge amount of cancellations, because every mixed term that involves both an a and a b will be cancelled by another guy, and the only things that survive will just be a to the k plus 1 and the b to the k plus 1. Yeah? Okay, so if that isn't, I do. I'm sorry. Yes, everything here is k. Right. There we go. Yes, all of these things have power k. Thank you. Okay. Everybody happy? Yeah. So this thing, whoops, b to the k, because these all have power k. This is a true formula right here. Right. So let's think about what this expression actually is, because we're trying to understand this thing. So if we look at put it over here, what a minus b actually is, it is equal to 1 over zeta minus z plus h minus 1 over zeta minus z. Let's make a common denominator. So then that's going to be zeta minus z minus, I mixed it the wrong way. This is zeta minus z. So zeta minus z zeta minus z, and then this is zeta minus z plus h, like this, over the common denominator, zeta minus z plus h, zeta minus z, like this. All this stuff cancels. We have this cancels, this cancels. We have minus minus, so it's just h. So this is h over zeta minus z plus h, zeta minus z. Okay, that's what a minus b is. Yeah? Cool. So let's look at this expression here, and we want to replace this by just a to the k plus 1 minus b to the k plus 1 over h, right? Which means we're going to have to we're going to have to what? We're going to have to divide by this thing on the other side, right? Because what does this thing say? This says that h is equal to just a minus b times zeta minus z plus h, zeta minus z, like this. So if we just divide by h like this, then well, okay, let's do it this way. So this thing we could multiply top and bottom of this thing by this thing over here without changing anything, right? If we multiply top and bottom of this thing by the red box, then we don't change anything, right? But then that would give us h underneath, right? So then we would have zeta minus z plus h, zeta minus z times a to the k plus 1 minus b to the k plus 1 over h, right, is equal to everything over here. Yeah, so this is equal to this. Yeah, give me a thumbs up if you're with me still. Make sure your thumb reaches the video camera. I can't see it. All right. Good. So if we want to understand just this expression divided by h, we're going to divide through by this stuff. Yeah? We're going to divide through by this stuff. Yeah? So running out of space here. So then this implies that a to the k plus 1 minus b to the k plus 1 over h is equal to all of that stuff is equal to all of this stuff, a to the k plus a to the k minus 1 times b plus blah, 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 a1, b to the k minus 1 plus b to the k, yeah? And now we're dividing through by this other stuff, right? By this zeta minus z plus h, zeta minus z plus h, zeta minus z. Yeah, and that finally is the expression that we want, because that's the thing we're trying to analyze here, right? So now let me put the blue box including the h again. So this stuff in the blue box is exactly this stuff. Yeah? It's exactly this stuff. Cool. Let's look at this expression. So what do we have? All of these things here, right? We have a is zeta minus z plus h. This is zeta minus z, yeah? And then here we have zeta minus z plus h, zeta minus z. So as h gets very, very small, this is more and more like zeta minus z, yeah? So all of these expressions right here, yeah, will ultimately in the limit be of the form 1 over zeta minus z now to the power k plus 2. Yeah? Because this is power k, this is power k, this is another one, this is another one. Yeah? So every single term inside this sum, as h goes to 0, will tend to the expression 1 over zeta minus z to the k plus 2. Do you see what I mean, people? Yeah, absolutely. So if we look at this guy and this guy, you know, then every expression inside this sum, you know, is some mixture of powers of this and powers of this, where the sum of the powers is equal to k. Yeah? And then we're dividing through by another couple of these guys. Yeah? So all of the terms inside this sum will ultimately be 1 over z minus z to something times z, 1 over zeta minus z to something times zeta minus z plus h to something, where the something plus the something is k plus 2. Yeah? Cool. All right. So that being the case, we have that this thing, as h tends to 0, will tend down to the following thing. So let me erase this. So this thing will tend to, how many terms do we have? We have k terms involving a and then another term. So it's k plus 1 terms altogether in this sum, yeah? So we have k plus 1 terms, and each one of these individual terms tends to this expression zeta minus z to the k plus 2. Yeah? Cool. Yeah? And what's even better about this is that we have an explicit formula here, yeah? So that we can see that this stuff will tend towards this thing, yeah? Uniformly for all zeta around the outside, so long as we let h be small enough. Yeah? Because we have these explicit expressions. We can show that for every single one of these explicit terms right here. Yeah? We can show that for each one of these explicit terms that it will tend to 1 over zeta minus z to the k plus 2, yeah? With some very small error, yeah? Uniformly for all zeta going around the circle, yeah? And therefore it's true for all k plus 1 of these terms. And that's how we can show the uniform convergence, which is the main issue we have to work with or get around. Is that making sense? So the point of this is to explicitly show that the partial differences tend uniformly to the derivative by explicitly finding an expression for the partial differences. That's all that this is doing. Yeah? Do you see what I mean? All right, give me a thumbs up if you are clear here. Okay, if it's not clear, then watch it again. Watch this explanation again on YouTube. Then talk with me in office hour, and we'll go over this. Make sure you're clear on what's happening. Okay, so we're at the point of showing that this tends to this expression, right? As h tends to 0, and my claim is that we can have this uniformly be true for every zeta inside the circle. Yeah? So that means that we can pass to the limit through this thing. And I'll show that in a second. I'll show you that if something converges uniformly on something we're integrating over, then we can pass through the limit easily. So if we do pass to the limit, if we can take the limit as h, we'll have the limit outside here, and if we can pass it inside the integral, then the limit of this thing is just this thing. Yeah? And that's exactly the formula we want, because then the k plus 1 goes here, k plus 1 factorial, yeah? And then we have this zeta minus z to the k plus 2. Yeah? So this lengthy expression here, this trick from calculus 1, allows us to do this job, allows us to show this inductive step that if the thing is true for the kth derivative, then the thing is true for the kth plus 1th derivative. Yeah? And again, just because we can explicitly write out what this partial difference is. So when I say partial difference, what I mean is this x plus h minus f of x over h. This is a partial difference. It's not the derivative yet. It's the partial difference. Yeah? Or it's the difference quotient, whatever. Yeah? And what we're allowed to do here is to show that this thing is uniformly converging to its derivative independent of zeta. Okay? All right, so I'm going to raise the board. I'm going to show you why uniform convergence allows us to pass through the limit, and then that will complete the proof. How are we for time? Oh, we're nearly out of time. All right. Okay. Claim. Given sequence, let's say fk from, say, omega into the complex numbers, doesn't have to be holomorphic, just any sequence, such that, or let's do also this, and curve gamma contained within this thing, and f from omega to the complex numbers, such that on the curve itself, we have that fk tends towards f uniformly. So the supremum of fk of z minus f of z, z belongs to the curve, tends to 0, right? That's the definition of uniform convergence, statement unit convergence. Then the limit of the integral over the curve of fk, the zeta, is actually equal to the integral of f of the z. In other words, we're passing the limit through, because the limit of fk is f, right? So we have the limit outside, and here the limit is inside. Yeah? Yeah. And why is that true? Because if we just look at this thing, look at the difference between these two things, fk of z minus fk, like this, dz, absolute value. Yeah, we can take the absolute value inside the integral, as we've learned, right? So that's less than the integral of this thing. Well, we actually have exactly the statement that we need, because we've learned that this thing right here is less than the length of the curve times the supremum of this thing over the curve, right? So that's exactly a statement that we proved earlier. So this is less than or equal to the length. Length of the curve gamma times the supremum of over gamma of this thing we have inside fk minus f. All right, if you look back, that's exactly the statement. So what's that saying? It's saying that this thing, since this is tending to 0, so take the limit as k goes to infinity, all the stuff in the absolute value is equal to 0, and absolute value is the absolute value is continuous itself, so that implies that the limit as k tends to infinity, this thing. I can put the absolute value signs if I want, but it's not necessary. Just out of consistency, minus the integral of this equals 0. All right, the absolute value of this number is 0, i.e. it's 0. Yeah? So this thing is equal to this thing. Yeah? Whereas from here to here, we just use the fact that the absolute value is a continuous function. Right? Cool. All right. And that's exactly our statement. That's exactly this statement. So if we have a sequence of functions on the curve that is uniformly converging to a limit, yeah, then passing through the integral is no problem. Passing the limit through the integral is no problem. And that's the thing that we had to be careful with. That was the reason for this, again, that was the reason for this expansion that we wrote in the AK, BK, whatever. Yeah? And if we didn't have to do that, then, if we didn't have to be careful about that, then we'd have a very simple proof just by looking at the derivative of the function I wrote up. Yeah? Cool. Yeah? All right. So actually, the heart of the proof is just this. You can recover the formula rather easily just by looking at this expression, noticing that you have the difference quotient, and then just taking the derivative of the function that gives that difference quotient. Yeah? And you see the exact expression for the Cauchy integral formula for derivatives. So the formula should seem quite natural when you do that for yourself. So when you're revising this topic, that would be the thing I would do first, is convince yourself. Just write out that difference quotient and then convince yourself of the formula by saying, what if I just passed through the limit happily without thinking about it? Then I would get what I need. Huh? And then from that idea, you go, okay, well, you have to work more carefully to make sure I can pass the limit, and then that's all the other stuff. So basically, all the other stuff was just sort of technicalities. It wasn't really important. Wasn't really that deep. It was just working hard to make sure we have no issues. But as I said, is when you have a bit more experience with this kind of stuff, you could just look at that expression and go, since the function I'm differentiating it's got higher order derivatives, it's clear that the partial differences will tend uniformly to the limit, independent of any zeta. So it's not a surprise that the theorem holds true. All right, is everybody happy? All right, have a good day, people. I will see you all next Tuesday.